Hello, AP Physics 1 students. I just want to look at some of the more interesting aspects of problem number 22 in our packet of problems on rotational motion. If you haven't looked at it yet, just give it a quick read through. Okay, seems like a pretty standard sort of problem, except it almost seems like it's written in reverse, right? Because part A asks you to find the kinetic energy, and to find kinetic energy, you have to find the speed, right? And then part B asks you to find the speed, and to find the speed, you have to know things like, the radius and the period. Think about tangential speed is 2 pi r of capital T, and you're given the radius, you have to know the period. And then letter C asks you to find the period. So it's almost like it's written in reverse. And to be quite honest, if you wanted to do this entire problem in reverse, you could. And at the end, I'll talk about how you could do that. But I want to try to do it in this order. I want to show you how you are fully capable of doing it this way, just with a little bit of a trick to it. Okay, so right off the bat, you should be able to find the kinetic energy without finding the speed. How can you do something like that? Well, it's a rather non-intuitive step, so I'm going to show it to you. When we did Kepler's laws, we started off by first saying that Kepler figured out that the planets go in elliptical orbits, and most orbits are elliptical as well. And then by the time we did the third law, we said, well, let's just pretend they're really circles, because it turns out while the planet's orbits are elliptical, they're very, very close to being circles, and most orbits are also pretty close to being circles. Like in this case, the moon, Ganymede, going around Jupiter is pretty much a circular orbit. At least it's really close to it. So we're going to start with that assumption. And when we did Kepler's third law, we said, well, if it's going in a circle, that means that the centripetally pointing force is only provided by the gravitational force. So let's start with that in our derivation here, that the net force, the centripetal force, is the gravitational force. Okay, and then just like we did on the derivation for Kepler's third law, we'll just substitute the equations. For the net force, that's just mv squared over r. And for the gravitational force, it's Newton's law of gravity, big G, big M, little m over r squared. When we did Kepler's third law, we manipulated this further to try to solve for that ratio of period squared to radius cubed. Let's not do that. Here, we're trying to get kinetic energy. So what can we do? Well, immediately you can see one factor of r goes away. Sure. And you might be tempted to say, well, one factor of m goes away too. The little m goes away, and that's the mass, in this case, of Ganymede, where capital M is the mass of Jupiter. And that's exactly what we did when we did our derivation of Kepler's third law. But let's not do that. Let's leave it in there. So you might say to yourself, well, why would we do that? We can clearly cancel little m. Sure we can. But remember what we're looking for. We're looking for kinetic energy. And the equation for kinetic energy is, of course, 1/2 mv squared. This already has mv squared, doesn't it? Right? So all we have to do then is just, well, divide by 2. If we divide this by 2, that is kinetic energy, right? mv squared over 2. And if we divide the left-hand side by 2, then we just divide the right-hand side by 2, which means this must be kinetic energy. It has to be. That's what the algebra says. And this is all stuff you can put in. We were given r, the orbital radius, big G, of course, we know. Little m is the mass of Ganymede, which you can find from another problem. It's given in problem 21. And then the mass of Jupiter is given in problem number 19. So those are all things you can look up, or if you don't want to look up in the problem set, you can look it up online. Okay? And so you can literally calculate the kinetic energy without knowing the speed. Fantastic. Now letter B asks you to find the speed. Now, of course, now that you have the kinetic energy, you can just substitute that in and solve for V, or if we just take the derivation we just did and pause it at this moment, well, we can solve this for V, right? And maybe it's more complicated, but I also just want to show you can do it from here as well. At this point, yes, of course, we would cancel little m, which in this case would be the mass of Ganymede itself, and then just take the square root, and this is also an expression for the speed of, in this case, the moon orbiting Jupiter, where capital M is the mass of Jupiter. And then from here, you can solve for letter C by saying, well, we just found the tangential speed, set that equal to 2 pi r over capital T, and solve for the orbital period. Or you can use Kepler's third law. Because remember, Kepler's third law, period squared over radius cubed, is a constant, only dealt with the mass of the central body. What's the central body here? It's Jupiter, which again you can use. Mass is given in problem 19. And so you could do part C first, if you wanted to, solve for the orbital period, then work backwards to part B, solve for the tangential speed, and then work backwards to part A and solve for the kinetic energy. And guess what? You're going to get pretty much the same answer regardless. Totally up to you how you want to do it, but I showed you this because I think it's worthwhile, and it's interesting, and it's pretty nice to look at.